this lesson we will be discussing Le Chatelier's principle. Le Chatelier's principle is a foundational, very important concept within the topic of chemical equilibrium, so we better get to it. Le Chatelier's principle states that for a reaction at equilibrium, any change to the system will cause the reaction to run in a direction to reduce the stress. We'll go through several iterations of what this means and how this plays out. The way that my chemistry teacher talked about it, if the system is happy or at equilibrium, anything you do to the system is not going to like. So if you do anything to it, it's going to say, ouch. And then it's going to try to undo what you just did. So you do something, it doesn't like it, it runs in a direction to undo what you just did. So here is our example that we'll be focusing on in most of our examples for this. Let's say that we are going to take this system, this reaction at equilibrium, and let's say that we're going to add some water to it. Now, this is gaseous water, so picture it as steam. So imagine a container that's sealed off. It's got this reaction happening, and we're going to add some water to it in the form of gaseous water, steam. So the possibilities, here are the possible answers. One of three things is going to happen. When we add that steam, either the forward reaction is going to increase. We say that the forward reaction predominates, is favored, lots of different ways, but the net takeaway of it is that more products will be made and reactants will be used up. Things on the right will increase, things on the left will decrease. Another possibility is the opposite. We could see that our change to the system causes things on the left to increase and things on the right to decrease. We would say the reverse reaction predominates, or the reaction runs to the left, or reactants are favored. All of those are different ways of saying the same thing. Third option is, of course, that we could add a bunch of something to this and nothing could happen. That is the other possibility. So let's see what's going to happen whenever we add our water. So the stress, the change, is that we've added water. We're going to add water. So the system says, ouch, you added water. I don't like that. So I'm going to remove the water. And the way that it removes water is it uses the water up by running to the right. Remember that as the reaction runs to the right and creates these things, creates products, it uses the reactants to make them. So if we add water, so our change was add water. So the system, or the reaction's response, is, hey, I'm going to use water. Use water. So the way that it does that is running to the right. So in that scenario, the addition of water, the system will run to the right. Products will be favored. Lots of ways that we can say this, but the net effect is that all of the things on the left will decrease in concentration and all of the things on the right will increase in concentration. So what are some other scenarios? Another scenario we might have is that we might remove hydrogen. Let's say that we remove, as it makes up the hydrogen, we remove it. So the stress is that we remove hydrogen. So the response from the system is the opposite. What is the opposite of remove? Add hydrogen. So hydrogen being a product, hydrogen being on the right, means that this reaction is going to favor going to the right. So in this example, we're going to make more hydrogen. So that is our first scenario. Now, what about some other, I guess that's not our first scenario, but It is the first new scenario. So let's say that we want to do something else, and let's say that we, instead of removing hydrogen, let's say that we remove water. Well, you might be able to intuit the answer here because we already did an add water, so let's see how this plays out. So let's say that we remove water. So that we remove water, system says ouch, and so its response is add. It's always add water. It's always going to be the opposite. So which direction makes water? Running forward uses up water and makes hydrogen. So if we want to make water, we're going to run the opposite way. We're going to add water by using these things on the right up. So in this scenario, products will decrease, reactants will increase. Now, one last example of this before we go on is, let's talk about removing some iron. You got to be careful with this one because assuming that there is some iron still in there, when we remove the iron, the iron, you would guess, is going to increase because we removed it, so it's going to increase. But the problem with that is that we have this little solid. You got to be careful of things that are solids and liquids in these gaseous equilibria because they don't actually participate in causing stresses usually. So if we add a bunch of iron solid to it, we are not necessarily going to get a change because it's not going to change the number of collisions in the bottle. So really, we only want to look at gases or aqueous ions as we look through these. So if you ever get a problem where it's doing changing some solid in the reaction, you can pretty much assume that there's not going to be an overall change in the equilibrium. So, let's go on to some other scenarios. What if we consider that the reaction is exothermic? So if it's exothermic, what does that mean? It means that it's going to produce heat. It's going to make heat. So heat is a product in this scenario. So if the reaction is exothermic, heat is a product. So we can kind of think of it this way. Now, when heat is a product, we can actually think of it as treating it for Le Chatelier's principle purposes in similar ways to the way that we would treat reactants. So what would happen if we put this reaction into a freezer? If we put this reaction into a freezer, then that would tend to remove that heat, right? Putting things in cold places makes them cooler, removes their heat. So if we put this reaction into a freezer, the stress, went ahead there. The stress is we remove heat. So the response by the system, according to Le Chatelier's principle, system says, ouch, you removed heat, so I am going to respond by making heat. So in this scenario, the reaction would run in the way that made more heat. It would use up the water, it would use up the iron, and it would make the heat. And so if you wanted to if say for some reason you happen to be running this reaction in a way so as to try to produce hydrogen, then you would want to run it in a freezer. If this were all true, this may not actually be an exothermic reaction. I meant to say that when I first put it up there. I didn't look up whether it is. It probably isn't. But if it's an exothermic reaction, then that would all work. So now what if we squeezed it? Well, if we squeeze it, that's a pressure change. We're going to be increasing when you squeeze something, like put a piston on it and push down. When you squeeze it, it's going to be making a higher pressure. So If I want to raise the pressure, then the system is going to want to lower the pressure. So the way that you think about this, well, what does pressure have to do with the reaction? Well, if we think about it, the system, the reaction can actually raise or lower the pressure in response to our stress by running to the side that has either more or fewer gas molecules, because after all, that is where air pressure comes from, is from gas molecules. So if we squeeze this system, it's going to run in a way that's going to make either more or fewer. Now, which is it? Well, if the system wants to make more gas molecules, if it wants to increase the pressure, it'll make more gas molecules. So increasing the pressure, put more gas molecules in there, would be what you would want to do if you were the system. If the system were looking for decreasing the pressure, then it would want to run to the side with fewer gas molecules. So if you look at this system as presented, you might say, well, okay, gas molecules, how do we count gas molecules? Well, you look at coefficients. So the coefficients here are 4 and 3 on the left, and 1 and 4 on the right, for a total of 7 on the left and 5 on the right. And so you would say, well, 7 has more gas molecules and 5 has fewer, but that would not be correct. You got to be really careful here, because one word I've said a whole bunch of times is gas. That's a gas molecule. That's a gas molecule. These are not gas molecules. We should not be counting those coefficients. We should only be counting that coefficient on the right and that coefficient on the left. So it's a tie. So actually this reaction is not going to run either way in response to a stress of pressure, because both sides, product and reactant, have the same number of gas molecules. So let's try, I guess I got there in fewer slides than I had made. So let's try a different reaction. Let's try a different reaction. This time, let's go ahead and let's lower the pressure. Let's lower the pressure on this system. So we lower the pressure, and so the system is going to want to raise the pressure. If we lower the pressure, the system's going to raise the pressure. So the system wants to raise the pressure. So the system wants to go to the place with more gas molecules. So we want to find the side with more gas molecules. So here we have this is a gas molecule. This is a gas molecule. I don't know why that didn't get printed in there. And then they're all gas molecules. So now we don't want to ignore any coefficients. So we have 4 and 5 for a total of 9 on the left, and we have 4 and 6 for a total of 10 on the right. So in this scenario, if we're going to lower the pressure, then the system is going to want to raise the pressure. So it's going to want to go to the side with more gas molecules. So lowering the pressure is going to cause this reaction to run to the right. It's going to cause water to increase. It's going to cause nitrogen monoxide to increase. It's going to cause ammonia to decrease and oxygen to decrease. So those are some various scenarios involving heat and pressure changes and addition and removal of products and reactants, and what Le Chatelier's principle says will happen in those scenarios.